Hello everybody, welcome to today's lecture. So today we're going to finish up 4.3 and then we're going to get into 4.4. So this video will wrap up chapter 4. Okay. We're not going to talk about 4.5. That section is about fitting a growth model to a problem, and it goes into some models that are more college algebra topics, which of course is not a prerequisite to this class. So it just kind of gets into the algebra side more than we want to in this class. It basically just takes the models that we've already done and then adds in the algebra topics, right? So we don't necessarily need to look at those since this isn't college algebra and we have different goals. Okay, so we're just going to do 4.3 and 4.4. So the last thing we left off on was talking about the doubling time model. Okay, so we ended with this topic right here. Make this a little, let me zoom out a little bit here. Okay. So we have that if D is the doubling time of a quantity, so D is how long the quantity takes to double. P0 is still the initial amount, right? T is still the time. It doesn't have to be in years anymore, but it's whatever unit of time we're working with. Then the doubling time model is given by this. Okay. This is P of T is equal to P sub 0 times 2 to the T over D. Okay. And we derived that from this example about bacteria where the population doubles in 5 days, but maybe we want to know how many bacteria are present after 1 day, or in our case, 14 days, right? Which isn't a multiple of 5. So how do we handle that? And then that's how we came up with this model. Okay. So let's do another example with this model here. Okay. Let's say this is example 4.3.4, but I'm going to alter it slightly. It's again about bacteria growth because the doubling time model is used for bacteria a lot because that's how bacteria colonies grow. If we just think about why that's true, right? A bacteria, the way it reproduces is asexually. It splits into two different bacteria, right? So this one bacteria splits into two. So then each of these bacteria will split into two, right? So at step 1, we have one bacteria at bacterium. At step 2, we have 2 bacteria. At step 3, we have 4 bacteria, right? And then it would be 8, 16, etc. So it's doubling every time. So this is why this model is applied to bacteria a lot. So suppose that a bacteria population doubles every 6 hours. Okay. This is much quicker than the last problem where in that case, the bacteria population doubled every 5 days, right? So in this one, the population doubles every 6 hours, which is much quicker. So if the initial population, and again, I'm altering the problem a little bit. So if the initial population is 4,000, then how large is the population? Okay. After, let's go with 24 hours. Yeah, why not? Okay. How large is the population after 24 hours? Okay. So The book instead asks you how long it takes to grow to a certain population, but that's using logarithms, which again isn't covered in this class, so we're going to skip over that part of this. So let's look at our model and try to identify the parts that we're given here. Okay, so this is our model. We know P sub 0 is the initial population, right? So we're given that as 4,000. We don't have to worry about R anymore because the R is always going to be 1, so that inside the parentheses is always going to be 2. We know T is going to be 24, right? And then we know D, this is how long it takes to double, which is given to us as 6, right? Assuming that we're using hours for our time unit, which we are because both things are given in hours. Okay. We do need to be a little bit careful about the hours because what if it asks how large population is after 1 day, for example, right? We would need to convert that to hours. Okay. We need to make sure T and D have the same units. So when we plug all of this in, P of 24, so the population after 24 hours, is going to be 4,000 times 2 to the 24 over 6. Right. Okay, so just plugging everything in here. We can simplify this a little bit right off the bat because 24 over 6 is actually just going to be 4. Okay, so so that one simplifies nicely. We don't actually have a fraction in the exponent once we simplify because it gets 4 chances to double, right? It does it every 6 hours, 24 hours. This is basically 1/4 of a day, right? So it gets 4 chances to double. So when we do that, 2 to the 4th is 16. So this is going to end up being 4,000 times 16, which I believe is 64,000. Okay. Let's check the math on that. 64,000. Okay. So this is how we use the model. Okay. So this gives us a little bit more leeway than the initial model, the initial exponential growth model, right? Which we could see back here, right? We could do something like the T over D thing in this model, but it's not as well defined because this is specifically talking about how often it doubles, right? So we've kind of seen something similar to that where we alter the T in the compound interest examples where we were multiplying it by n, right? So we're kind of doing the same thing, except for in this case, we're dividing. We're altering the T a little bit though. And this allows us to look at different time intervals other than just the ones that were given, right? We don't have to look at just 6-hour time intervals. In this case, we did, but we could just look at how many bacteria are there after 8 hours or something like that, right? It doesn't have to be a multiple of 6. Okay. So it's a little bit more powerful, but it has the restriction, of course, of that it's only working for doubling, right? Okay. So the last thing we want to talk about with doubling time, I just want to mention it really quickly. I don't even really want to go into it. Is what's called the rule of 70. Okay. So this is a formula for approximating the doubling time. Okay. So as the book mentions, like I just said, this is a rule for approximating doubling time. And It is an approximation for growth rates less than 15%. Okay. Oops. So this can only be used as an approximation for growth rates less than 15%. Okay. Now this is being used a little bit different than before, right? In the problems before this with the doubling time model, our growth rate was always 1 or 100%, right? But this is instead calculating, when it's talking about approximating the doubling time, it's talking about the time in which it takes to double. Okay. So that was given to us in the previous problems. Like in this one, it says that the population doubles every 6 hours, right? And in this one, it said that the population doubles every 5 days. So it's approximating that quantity. Okay. So this will only work if our R is 0.15 or smaller. Okay. So R, it actually uses a capital R. Well, I'll use a smaller R because what the rule uses is it uses capital R because it doesn't actually convert the percent to a decimal. Okay. Usually we have to convert the percent to a decimal, but in this case, it actually is just using the percent as the exactly as it is, right? So 15. So they use a capital R to kind of signify that. Okay. So the doubling time, let's just write D because we already established that that's the doubling time. The doubling time is approximately, which is what the squiggly equal means, approximately equal to 70 divided by R. Okay. Where R is the growth rate percentage. Okay. So it's not converted to a decimal. And D is the doubling time. So again, I just kind of wanted to mention this. It's not like a question I'm going to ask or anything, but it I've seen it come up before, just in like random things. So I thought it was worth mentioning, but I just don't really want to get into it too much because it is just an approximation, right? Um, so this would just be to do something quick. The better way to um, figure out the doubling time would be via a little bit of algebra. We would need logarithms for something like that, which isn't covered in this class. So this is a way to do it when, we have no other option. So just to look at an example real quick, I'll just kind of shorten the problem a little bit. It says that a bird population grows by 2.5% annually, right? So it's lower than 15, so we can use it. So all we want to know is what is the doubling time, right? What is the approximate time that it takes the bird population to double? Okay, so D is going to be approximately 70 divided by 2.5. Okay. So we can throw this in our calculator. And we'll get 28. Okay. So the bird population will approximately double in 28 years. So then the second part of the problem says, if the initial population is 20 birds, then this tells us that after 28 years, it's going to grow to 40 birds. Okay. So this is an approximation for how we get the doubling time. Okay. So let's move on to the next part now. Like I said, this was just like a little aside. The more important part of this section is the doubling time model and like that first example we did. Okay. So I'm going to kind of split it up here because this is where the like second half kind of starts. Okay. So next we want to talk about exponential decay. And half-life. Okay. So exponential decay is kind of the opposite of exponential growth, right? With exponential growth, you have the models that look like this, right? Where they are, they don't start out growing very quickly, but then they start growing quickly really fast. Exponential decay will kind of be the opposite, right? Where it will start falling really fast and then it'll start to level out. Okay. And we already kind of saw examples of this before, right? Okay, so back in the one of the examples we did for exponential growth, I believe, yeah, example 4.2.5, where we were talking about the population decay in Puerto Rico, right? We talked about the population decreasing. So this is exactly the same kind of thing. Okay. So let's look at what the half-life, what's called the half-life model is. Okay, this is an example of exponential decay. So with doubling time, our inside part was always 2, right? So with half-life, the inside the parentheses part is always going to be 1/2. So it's kind of the opposite, where with the doubling time at every unit of time, um, it was doubling, right? In this case, it's at every unit of time is being halved. So it's kind of the same idea, but going in the opposite direction. So this is usually used with like chemicals, right? Um, like um, in something such as like carbon dating, right? In order to find out how old something is, one thing that archaeologists or scientists will do is they will measure the amount of carbon that's in something, and they can use that plus the fact that they know what is called the half-life of carbon, which is how long it takes for half of the carbon in something to go away, right, to leave it. And they can kind of reverse engineer to see how old it is. Okay, so the half-life tells you how long it takes for half of that chemical or element to leave, right? To decay, to go away, right? So if you start with like 50 milligrams of something and it has a half-life of 1 year, then after 1 year, you'll have 25 milligrams. And then after 2 years, you'll have 12.5 milligrams, right? And then after 3 years, you'll have 6.25 milligrams, right? It'll keep halving every time. Okay. Now notice when it keeps halving like that, it's never going to reach 0, because if you keep multiplying it by a half or dividing by 2, you can never get to 0, right? It's just going to keep getting smaller and smaller and smaller. So, the people dating these, they would need good instruments to detect very, very small amounts of these elements. Okay. So the half-life model is going to be very similar to the doubling time model, where it's going to be P of t is equal to P sub 0 of 1/2 to the t over h. Okay. So just a couple of key differences from the doubling time model. One, the inside part is 1/2 instead of 2 because it's being halved every time instead of doubled. And the exponent, the d was replaced with an h, but it really means the same thing. The d was the amount of time it takes to double, and in this case the h is the half-life, or the amount of time it takes to halve. Okay. So h is equal to the half-life that's the amount of time something takes to have. I don't know if you can use half as a verb like that, but we're going to. Something takes to half. And everything else is the same, right? P0 is the initial amount, T is the time. Okay. So again, this is just something I kind of want to mention again, like these kind of examples are way less important than the doubling time examples for our case, because this is really only relevant like if you're going to go into like chemistry or biology, and if you are, you'd probably study this more in depth in those classes, right? So it's just something I kind of want to mention so that you're aware of it. We can do an example with it, but I'm more focused on the doubling time model because we can see some practical uses for that more easily, and it's basically the same thing. Okay. So we can just do like the first example here, 4.3.9, where it says that lead 209 is a radioactive isotope. Okay. So it's, isotopes, which we won't really get into like the definition of those because I don't really know it that well. um, but these are the kind of things that usually are associated with half-lives, right? Like carbon dating, I believe, is specifically carbon-14. So that's one of the isotopes of carbon that's used. I actually read recently that carbon dating isn't so popular anymore. That's usually used with different elements. But still, that's usually the one we learn about first in science classes. Okay. So anyway, so lead 209 is a radioactive isotope. It has a half-life of 3.3 hours. Okay. So every 3.3 hours, there's only half of it left from whatever the initial time was. Okay, suppose that 40 milligrams of this isotope is created in an experiment. So 40 milligrams is created in an experiment. Okay. How much is left after 14 hours? Okay. So just like with it's the same thing as a doubling time model, just with slight variation. Okay. So we just again want to identify our variables. So we're given that we start out with 40 milligrams, right? So P sub 0 is going to be 40. Then we're given that the half-life is 3.3 hours, right? So that's H. And then we're given that T, the time, is 14 hours, right? Again, we need to make sure those units match as well. And in this case, they do. So P of 14, in other words, the amount left after 14 hours, is equal to 40 times 1/2 to the 14 over 3.3. Okay, so we'll need our calculators for this one because we're going to have a decimal in the exponent here. So 14 divided by 3.3 is 4.24 repeating. So we're going to do 0.5 raised to that. I'm just going to do 0.5 raised to 14 divided by 3.3, put the whole thing in the exponent so I don't have to round here. When I do that, so when I do this part right here, I get 0.0528, okay? And then we want to multiply that by 40. So we'll get approximately 2.11 here. Okay. So approximately 2.11 milligrams of lead is left after 14 hours, right? So it decays really quickly, right? So if you don't get to it until after a couple of days, you need to be able to detect very small amounts. Yeah. Okay. So that's all we do there. The book goes through a lot more examples with different isotopes. It even talks about carbon-14 in example 4.3.11, which is what I was talking about a little. Then it goes over the rule of 70 for half-life, just like we did for doubling time. It's pretty much the same thing. It's talking about approximating the half-life of an element, again for decay rates less than 15%. So it's has the same rules as the doubling time. And then it ends the chapter by going over some rules of exponents and logarithms. Okay. The exponent rules I would expect you to know, but you don't really need it for any of these problems because most of the time we get away with just putting the problems in the calculator. We haven't really had any need to do anything with the exponent rules, even though it's technically a prerequisite for this class. So, I wouldn't really worry about it too much. And then the logarithm rules, if you're curious, they're listed here in the book. This allows you to solve a greater variety of problems, like if you want to solve for t, for example, right? Which oftentimes we would. We want to solve for the time. For example, for doubling time, maybe we want to know how long it's going to take our money to double, or how long it's going to take our money to reach a certain amount, right? For that kind of stuff, we would need logarithms. So if you're curious about it, the book goes through it at the end here, and it did plenty of examples where it used those as well. Okay, so we are going to move on to 4.4 now, though. So 4.4 is about natural growth and logistic growth. Oh, you can actually see I have a little bit written here already. You can get rid of that and start fresh. I didn't realize that was in there. Okay. So I'll write this all larger. Okay. So natural, whoops. Let me do this here. Natural. Sorry, I think I need to like zoom in. So it was so small. Let's try that. Natural. There we go. Growth. And logarithmic growth. Or sorry, no, it's logistic growth, not logarithmic growth. Yeah. So logistic growth is referring to logarithms, but we don't actually need logarithms to do the problems, luckily. Okay. But natural growth, whenever we see the word natural in math, oftentimes it's implying that we're using the number e. Okay. So hopefully you remember this number from 5.3 when we were talking about continuously compounded interest, right? We had p e to the rt for our continuously compounded interest formula. I can go back and show that for a second here. Right at the end here, right? You can see it right there. So just as a reminder, like it says right here, zoom in. E is not a variable. E is a number, kind of like how we use pi to signify a number, right? The Greek letter pi, we use our letter E to signify this number, which is about 2.718. It stands for Euler's number. Euler was the guy we studied in graph theory. Or sometimes it's just called the exponential number because it shows up in exponent a lot. So that's going to be the same case here. Natural usually implies that it has something to do with E, as E comes up naturally, right? So the natural growth model the natural growth model, just like the interest rate one, when we talked about continuously compounded interest, the E replaced the 1 plus R over N part. The R still got included there. The natural growth model is going to replace the 1 plus R part of the compound growth problem. Exponential growth model. Okay. So we're going to have P of t is equal to P sub 0 still times E to the KT. Okay. So this is very similar to the continuously compounded interest model, and it's really identical. Okay. It's using K instead of R, but it kind of has the same function, right? Just like the E replaced the 1 plus R and moved the R to the exponent here. E replaced 1 plus R and it moved it to the exponent, but now we call it K instead. Okay, just because that's just what's used when we talk about populations more often. Okay. There's really no reason to even call it K. Like you'd be perfectly fine calling it R, but this is what the book calls it. So, we'll stick with the book notation. So let me zoom in a little bit more here. The population, the P sub 0 is still the initial population, just like before. E is a number, which is approximately 2.718. Okay, you can just replace E with 2.718 in all of these if you wanted to. Okay. K is the growth rate. T is the time. Okay. So K has the exact same function that R did. Okay. Okay. So let's do example 4.4.2. Okay. This says that Bob discovers an anthill. I'll just kind of give the cliff notes of the problem. Discovers an anthill with about 100 ants. Okay. the ant colonies with the right conditions, it says the ant colonies have a growth rate of about 240% per year. Okay. So it says, how many ants will he have after 1 year? Okay. So this kind of gives a good example of what kind of problems this is used for. It's used for like a natural growth, right? AKA like things that would come up in nature, like ant populations growing, right? It's often used for human populations as well. Um, so a lot these problems really are going to look exactly like the continuously compounded interest problems, where you have to identify the rate and the initial population and the time, and then plug it into the exact same formula. Okay, so we could pretend this was about money. We could pretend it's like $100 with a growth rate of 240% and after 1 year, and it will work the exact same way. Okay, so anyway, let's look at our variables, right? So our p sub 0, right, this is the answer. P sub 0 is equal to 100. That's the initial population. Our k is 240%. We need to put it into a decimal, so it's actually going to be 2.4. Okay. It's a lot larger of a growth rate than we're used to. So be careful with that. And then t is going to be 1, right? Because it's after 1 year. So our formula will be p of 1 is equal to 100 times e to the 2.4 times 1. Okay. So e to the 2.4 we'll definitely need the calculator for. So your calculator should have an e to the x button. Okay, so we can do e to the x and then 2.4, or I think on iPhones it's backwards where you do 2.4 and then you press e to the x. So when you do that, you should get 11.023, and then we're going to multiply by 100 to get approximately 1102. Okay. So after 1 year, we'll have about 1102 ants. Okay. So we're done with the natural growth model. Okay. So now I want to get into, so the natural growth model is kind of another special case of the exponential growth, right? So we kind of have 3 special cases: the doubling time, the half-life, and the natural growth, right? But it functions the same way, right? It's kind of just like using e as your 1 plus r instead. Okay. So now we're going to finally get into the last overall model. Going back to 4.1, we talked about how there are 3, right? There's the linear growth, the exponential growth, and the logistic growth. Really, there's a lot more than this, but these are the 3 that we're focusing on. So we're going to talk about the logistic growth model now. So the logistic growth model, you can see how we drew it in 4.1. It's kind of the inverse of the exponential growth model, where it starts out growing very quickly, but then it starts to level out. Okay. So it has built into it what's called the carrying capacity. The carrying capacity is the largest population that can be sustained. Okay. So it's like the largest number of people it can carry or organisms it can carry. So you can see right here when it starts to level out, that means it's approaching the carrying capacity. And it typically never actually reaches the carrying capacity. It just gets closer and closer to it. Okay. So the logistic growth model, let's write it down first, and then we'll talk about the parts here. Is equal to P of t, so this is still the population after a certain amount of time, is equal to m over 1 plus k times e to the negative ct. Okay. So we got some new things here. E, right? First of all, this part looks very similar to the natural growth model. This part right here, it just has a negative exponent instead. E is the same thing as before, right? E is that 2.718 number. Okay. So these problems are a little bit different in that, typically the way that we give the problems is, we get some word problem and we have to identify the parts, right? Like here's the growth rate, here's the time, etc. But this one's a little bit different in that the model is usually given to you. Okay, so it's not explicitly laid out what exactly K and C are. Okay, and we can kind of deduce it going through the problems. It is explicitly laid out that M is the carrying capacity. Okay. Again, this is the maximum population that the environment can sustain. Okay. So like the world, for example, would have a carrying capacity. Eventually, human population is growing really fast, right? It's just if you look over the last like 100, 200 years, it's grown very quickly. But we have to imagine that eventually there is an upper limit to that, right? Eventually we would hit a carrying capacity for how many people could fit on the earth because there's only so many resources, right? And humans are pretty inventive and find ways around that. So maybe we'll never see it in our lifetimes. But we can see it with other organisms like other like mammals or something. Like you think of like mammals growing in like say the rainforest. There's a maximum population of animals that can live there because once it gets too large, they would be competing for limited resources, right? They have to eat other animals. Those other animals have a certain population. There's just not enough to go around, right? So there's an upper limit to how much of something that the environment can hold. So M ends up being this upper limit. Okay. What we'll end up seeing is that as our time gets larger and larger, so as you go further and further into the future, this whole quantity right here gets smaller and smaller. Okay. So eventually if it got infinitely small, it would eventually be 0, right? And then you would just have m divided by 1, which is m, so you'd reach your carrying capacity. Because, we can't think about infinity like that, it's never actually going to hit 0, so it's going to be 1 plus a little bit, so it's going to be m divided by something a little bit larger than 1. So overall, this number will always be a little bit less than m. Okay. So looking at the graph here, we can see it starts to level out. M is going to be like a line here that the graph keeps getting closer to, but it never actually touches. So, like I said, though, most of these problems will just have the model, the formula given to you. You don't have to identify the variables. So even though the formula is a little more complicated, it actually makes solving the problems a little bit easier because all we have to do is just put them in the calculator. Okay. So let's do the first example. This is about bird populations, which is that an endangered bird species grows according to the model P of t is equal to 3640 divided by 1 plus 25 e to the negative 0.04 t. Okay. So there's a few questions we can ask about this, right? 3640 is going to be the upper limit of the bird species. This is the carrying capacity. So before we can figure out the model, we have to know what the upper limit is. So that makes it pretty hard to come up with these models in practice, right? It's hard to know, for example, how many humans could fit on the Earth. But anyway, let's look at what the initial population is. How do we know how many birds we're starting with? Okay. So the initial population is going to be the population when time is equal to 0. So what happens when we plug 0 into this? Okay, we could use a calculator or we could just use our knowledge of exponents. Okay. If you know your exponent rules, we only really need one here because the bottom part here, negative 0.04 times 0 is 0. So what's something raised to the 0th power? Well, anything raised to the 0th power is equal to 1. Okay. So as an aside here, a to the 0 is equal to 1, except for if a is equal to 0. So if a does not equal 0. Okay, I'll just write that on the side. So 0 to the 0 is not necessarily 1, but anything else raised to the 0th power is equal to 1. Okay. So this is just 3640 over 1 plus 25, which is 26. Right, so we can do 3640 divided by 26, which is 140. Okay, so we're starting out with 140 birds. Okay. So then we can answer a bunch of other questions. We could look at the population after 5 years. Right, after 5 years, you have 5. You're going to have 3640 over 1 plus 25 e to the negative 0.04 times 5. Okay. So you really, it's all just putting in your calculator. You just got to be careful about how you do this. Okay. So it'd be a good idea to do the exponent first, right? Multiply by 5 by negative 0.04, which you should get negative 0.2 in that case. Then again, I think on an iPhone, you get the negative 0.2 and then you press e to the x. On an Android phone, it's the opposite direction. You press e to the x and then you do negative 0.02. So you should get 0.98 when you do that. That's just this part. Okay. And then we want to multiply by 25. So we're doing this part to get 24.5. And then finally add 1 to get the denominator. So at this part, we're at about 3640 divided by 25.5. Okay. And then finally, we can do 3640 divided by that. 3640 divided by 25.5 to get approximately 142.75. Okay, and it's just birds, so we can just round to the nearest whole number. So we'll just round to the nearest, so we'll just round to 143. Okay. Okay, so the book actually gets a slightly different answer than this. They get about 170. And I'm not sure why. I've checked the work a few times. Just looking at it again, I really don't see where the discrepancy is here. So, yeah, maybe if you got a different answer, please let me know. But they get 170, which does make a little bit more sense because after 5 years, your bird population probably hasn't only grown by 3, right? Growing by 30 makes a little bit more sense. So it seems like my answer here is off by about a factor of 10. I've done it a few times and I'm not seeing why. So maybe I'm just missing something. If we were in a classroom, I could ask if anybody got a different answer, but yeah, let me know if you got something different for this one. Okay. But yeah, the idea is just, be careful about how you put in your calculator, which apparently either I was not or the book was not. Okay. Okay. I think that's really all I wanted to talk about in this section, actually. Because all of the examples are going to be exactly the same. It's just plugging into this formula. Okay. What the book likes to go through, what kind of builds up to is the carrying capacity. I kind of just stated it outright, but the book instead has you put in larger and larger amounts of times, like 100, 500, etc. And then you see that it gets closer and closer to 3640. Okay. So, go ahead and do that. And if you put in like a million for T, for example, you're going to get a number super close to 3640, but it's always going to be just slightly less. Okay, no matter how large of a number you put in. Okay. Okay, so that concludes chapter 4. Um, so thank you for watching this, and I will see you next time.